Hello everyone. I want to formalize this IMO problem from 1964. I have come up with an informal solution and I think it works, but I guess we'll find out as we try to formalize it. So the problem is just to show that there is no multiple of 7 of the form 2 to the n plus 1. One thing I'm excited about tonight is that I'll be doing this in Lean 4. Mathlib 4, the port of Mathlib from Lean 3 to Lean 4 is moving along quite nicely, and we can now do a lot of Olympiad problems in Lean 4. The informal argument that I want to make has to do with this pattern that comes up. Let's make a little table here. n to n plus 1. So if n is 0, then this is 1 plus 1 is 2. Let's go mod 7, and I think you see the pattern. My proposal for proving this is just to define a little helper function and then prove that that function always lines up with this value mod 7. 2, 3, 5. Repeating n equals 2 to the n plus 1 mod 7. Induction of n. I have to type /period to get the right dot. We've got at least 4 different centered dot characters we're talking about here. Control U, Control X equals. Look at all that. So I think actually what I want to do is so the 0 case is just refl and IH. The fancy tactic I had in mind is called mod cases. I may need to import that. Gotta compile those leans. Mathlib tactic mod cases. Okay, does case disjunction on e mod n, where e is in the integers. Okay, I kind of want it on the natural numbers. Hope that's not going to be too painful. I'm just going to try this. I kind of expect an error because this thing expects nats, not ints. H n%3. Yep, there's our error. Do we translate this to ints or do we just do things by hand? I'm going to say let's do things by hand because I am more confident that that's going to work. And like what I expect to happen here is we'll do this cases n like 3 or maybe 4 times, and then well, no, we want to do cases of n%3. So if we want to do this in the integers, what would that look like? Okay, so int fast64t has a suggestion that does not need induction, which might be convenient. I'm going to try to go through with what I was doing first, and I'll consider that one if I get stuck or if I get bored after finishing this way. Mod cases. I'm just struggling with how to set this up so I can case analyze on n mod 3. What I know how to do, this is like completely ridiculous, is have exists n prime such that n prime equals n mod 3. That n prime is just n mod 3 itself. Unpack this at n prime, and then can I say cases n prime? Yeah, I think this gives us what we need. So we have n mod 3 is 0. We have that the thing we want is true for n. We want to prove that it's true for n plus 1. So what if I just say unfold repeating? Okay, so what I really want is that n dot sec and 1, right? I believe I can prove that. For all these cases, we're going to want to sort of do the same thing on this exponent. We're going to want to pull out a factor of 2. Okay, let's give ourselves a library search. Oh, it's just refl. I can definitely simplify this. Dsimp only. Definitional simplification. Nice. Okay. This also gives us enough information to plug in to get rid of this repeating as well. Unfold repeating at IH and rewrite HN prime at IH. Dsimp only at IH. I expect this IH to imply this. If 2 equals 2 to the n plus 1 mod 7, then 3 must equal to the n times 2 plus 1 mod 7. At a high level, what I'm going to do is add 1 to both sides. So this is 2 to the n times 2 plus 2. Then factor out 2, and then be able to substitute this IH in. I think the stuff that's going to let me do that is like add mod. I know there's a similar mul mod. Add mod. Okay. Before I get too deep in the weeds on this, I want to poke a little bit more at going into the integers. This is integer modulus. This is the integer 7. This is the integer 2. This is the integer 1. It's not even letting me say sorry. Sorry is supposed to always work. My sorry axiom has the wrong type. So I'm just going to chalk that up to the mod cases tactic maybe not being ready for prime time yet. That's pretty ridiculous. Try this such that n prime equals n. Maybe mod cases will be happier like this. Unknown identifier n prime. What do you want, man? To do fix mod cases in Mathlib 4. But I still ought to be able to cast this problem in terms of the ring z mod 3. then I'm a little bit worried that this zmod thing seems very underdeveloped. The only file that has been ported has been this basic defs file. We're unlikely to have what we need. I'm going to stare at this a little bit longer, then I'm going to maybe scroll up and consider IntFast64's approach. Tactic ruffle works, but term ruffle doesn't work. What I'm trying to do here is just massage this induction hypothesis to look more like the thing we're trying to prove. Rewrite H3 at H2. Wow. We're kind of getting somewhere, but I don't know if it's where we wanted to go. Deterministic timeout. Oh no. This is somewhat closer to this. Ring will do it. We know what this is, and we want to know what this is. So this is cool because this is exactly this. And maybe now is just the time to unfold the definition of mod. Let's forget all this. Becoming painful enough that I'm going to go back to think about IntFast64's idea. Very simple proof. Let me actually copy that from chat. Yeah, I like this. Let's make sure that we have the lemmas we need. There's this thing about commuting modulus operator and exponentiation. Math.powmod. Is that a thing? I suppose it is. Supposed to be times. Yeah, I think we can make this work. So step 1, n equals 3k plus j. I think that's actually where we use this div@mod thing. N integer divide 3 is the k, and n mod 3 is the j. Intro h. This is turning the addition in the exponent into multiplication down below. Powadd. Rewrite h2 at h. If it's a multiplication in the exponent, it turns into, we had 2 to the 3k, turned into 2 to the 3 to the k. And powmod is going to help us with this. Powmat? Powmol. Powmol. Now I just want to like move the modulus operator just into every term and then compute the ones I can compute. So this one I'll be able to compute. This is just 1, right? H3. Okay, and then 1 to the whatever is just 1. This is good. But we'll do the thing we always do, which is ask library search what the lemma we want is. 1 pow. Rewrite h4 at h. Clear h4. Rewrite 1 mol. Mol 1. Nat.1 mol. 1 times a equals a. Oh, at h. Got it. Another thing we can do is taking the modulus operator twice. It's idempotent. That will just collapse to a single application. Mod. And now has the time come to case bash? So just need to set up this case analysis. Kind of want to copy how I was doing it up here. Again, it's a little ridiculous, but I think this is a nice way to do it. And then we just case analyze on n prime. Cases n prime with 0, sorry, doc. And so in the first case, I guess in all of these cases, we'll just do like rewrite h n prime and then num at h. I think exactly that thing was going to work for all the cases. So let's do it again. Yep, worked that time. And one more that's going to be non-trivial. Okay, and then what we're left with here is going to be something where n prime is too large. N prime being this large contradicts with the fact that it's the result of the modulus operator. Not quite sure how we do that. I don't think this like norm num does it. Let's try library search. I just want to prove that a%3 is less than 3. There's probably a lemma that does this. Fin of nat proof 1a. That's like not something that's intended to be used. Maybe I can steal this proof. Nat.mod lt. Mod lt. If y is greater than 0. So we just need that 3 is greater than 0. 3 greater than 0 by norm num. Come on. Okay, that means library search failed. Oh, I just wrote that wrong. Okay. Oh, no, I just want this to be n. So yeah, so then my like transitivity, this triple successor thing is less than 3. That's going to be our contradiction. If we apply the successor 3 times, it's got to be at least 3. Rewrite hn prime at h6. Okay, that's definitely a contradiction. Can library search find something for us? Probably not. No. I mean, I bet Linereth can do it. Unknown tactic. Yeah, Linereth can do it. Definitely overkill. But we did it. Fireworks animation. Boom, boom, boom. Mario has reached the checkpoint at the end of the level. Triumphant music plays. Thank you, int fast64t, for the simpler proof. Credit to int fast64t. Now, is there any way we can make this a little nicer? We can do all this rewriting here in a calc block, which will make it look a lot cleaner. Well, maybe that's simple enough. Fits on one screen here. Yeah, I think that's about it for tonight. Thanks for coming out, everyone. See ya.